Good morning/afternoon, everyone. Today, I'm excited to share insights from Anthropic's engineering team about a powerful approach to building more efficient AI agents using the Model Context Protocol, or MCP. The core idea we'll explore is simple but transformative. Instead of having agents make direct tool calls that consume massive amounts of context, we can have them write code to interact with MCP servers. This shift can reduce token usage by over 98% in some cases, dramatically improving both performance and cost efficiency. As AI agents scale to interact with hundreds or thousands of tools, this approach becomes not just beneficial, but essential. Let's dive into why this matters and how it works. What is MCP? First, let me quickly explain what MCP is for those who may not be familiar. The Model Context Protocol is an open standard for connecting AI agents to external systems. Before MCP, connecting agents to tools was a fragmented landscape. Each agent tool pairing required its own custom integration. If you had 10 different agents and wanted them to connect to 20 different tools, you'd potentially need 200 different integrations. This created enormous duplication of effort and made it nearly impossible to scale connected AI systems. MCP solves this by providing a universal protocol. It's like USB for AI agents. Implement the standard once, and suddenly your agent can connect to an entire ecosystem of tools. Since Anthropic launched MCP in November 2024, adoption has been remarkable. The community has built thousands of MCP servers. SDKs are available for all major programming languages, and the industry has essentially adopted MCP as the de facto standard for agent tool connections. This success has been exciting, but it's also exposed new scaling challenges, which is exactly what we're here to address today. The scaling problem. As developers build more ambitious agents, they're connecting them to hundreds or even thousands of tools across dozens of MCP servers. This is where we start to see critical efficiency issues emerge. There are two main problems that arise at scale. First is tool definition overload. The typical approach is to load all available tool definitions up front directly into the model's context window. Each tool definition includes descriptions, detailed parameter specifications with types and requirements, and information about what the tool returns. Now, this doesn't look that bad for 2 tools, but imagine this for 1,000 tools, or 10,000. Some enterprise agents are connecting to that many systems. Before the agent can even start thinking about the user's actual request, it has to process this massive wall of tool definitions. The impact is significant. Your agent is essentially reading a small book's worth of API documentation before it can do anything useful. This increases latency, users have to wait longer for responses, it increases costs, you're paying for all those tokens, and it reduces the amount of context available for the actual task at hand. This is problem number 1, and it only gets worse as you add more integrations. Problem 2, intermediate results. Now let's look at the second problem, how intermediate results consume context. Here's a real-world scenario. A user asks their agent to download my meeting transcript from Google Drive and attach it to a Salesforce lead. Simple request, right? But look at what happens under the hood. First, the agent calls Google Drive to get the document. The full transcript, which could be tens of thousands of words, gets loaded into the model's context window. The model processes it. Then the model needs to call Salesforce to update the record. And to do that, it has to write out the entire transcript again as part of the tool call parameters. So that meeting transcript flows through the context window twice. For a 2-hour sales meeting, we're talking about 50,000 additional tokens. You're essentially paying for the model to read and write the same content multiple times, even though the model doesn't actually need to reason about most of that content. It's just moving data from point A to point B. And this is just a simple 2-step operation. Imagine a complex workflow with 10 or 20 steps, each passing large amounts of data through the model. The token usage balloons quickly. This is particularly problematic because these large intermediate results can also increase the likelihood of errors. Models might truncate data, make mistakes when copying, or simply run out of context space. Architecture comparison. Let me show you the traditional MCP architecture to make these problems crystal clear. The flow works like this. The MCP client loads all tool definitions into the context window. The LLM receives these definitions along with the user's request. When the LLM decides to use a tool, it makes a tool call. That call goes to MCP server, which executes it and returns the result. That result goes back to the LLM where it's added to the context. The LLM processes the result and potentially makes another tool call, continuing this loop. Every single operation in this flow passes through the context window. Every tool definition, every tool call, every result. The context window becomes this central bottleneck where everything has to flow through. Now, for simple agents with a handful of tools, this works fine. But as you scale up, this architecture creates increasingly serious efficiency problems. The context window fills up with tool definitions and intermediate data, leaving less room for actual reasoning. Processing time increases, costs escalate, and you start hitting hard limits on what's even possible. This is the fundamental challenge we need to solve. And the solution, it turns out, comes from a different way of thinking about how agents interact with tools. The solution. So what's the solution? It's actually elegantly simple. Instead of presenting MCP servers as direct tool calls, we present them as code APIs, then we let the agent write code to interact with those APIs. This might sound like a small change, but it fundamentally transforms the architecture, and it addresses both of our efficiency problems simultaneously. Here are the key benefits of this approach. First, progressive disclosure. Instead of loading all tool definitions up front, the agent can discover and load only the tools it actually needs for the current task. It's like having a library where you only check out the books you need rather than carrying the entire library around with you. Second, context efficiency. Data can be processed in the code execution environment, not in the model's context. The agent can fetch large datasets, filter them, transform them, and only pass the final relevant results back to the model. Third, better control flow. With code, you can use familiar programming constructs like loops, conditionals, and error handling. This is much more efficient than chaining individual tool calls through the model. Fourth, privacy preservation. Sensitive data can flow through your workflow without ever entering the model's context window. Only the information you explicitly log or return becomes visible to the model. And fifth, state persistence. The code execution environment can maintain state across operations, allowing agents to build up context over time and even save reusable functions as skills. The core insight here is that LLMs are excellent at writing code. We should leverage that strength to build more efficient AI architectures. Implementation, file tree. Let me show you how this works in practice. One elegant implementation approach is to generate a file tree representation of all available tools from your connected MCP servers. Here's what that looks like. You have a servers directory at the root. Inside, you have subdirectories for each connected server, Google Drive, Salesforce, Slack, and so on. Within each server directory, you have individual TypeScript files for each tool, plus an index file. This structure is intuitive and navigable. The agent can explore it just like a developer would. Want to see what Google Drive tools are available? List the Google Drive directory. Want to understand what the getDocument function does? Read the getDocument.ts file. The beauty of this approach is progressive disclosure in action. The agent doesn't need to load all tool definitions up front. It can navigate the file system, discover what's available, and load only what it needs. For an agent connected to 1,000 tools but only needing 5 for the current task, this means loading 5 tool definitions instead of 1,000. That's a 99.5% reduction in tool-related token usage right there, before we even start executing operations. Tool file structure. Now let's look at what an individual tool file contains. Here's the getDocument tool for Google Drive. It's a simple TypeScript file with clear type definitions. We define an input interface specifying what parameters the function takes, in this case just a document ID. We define a response interface specifying what the function returns, the document content. Then we have the actual function. It's a simple async function that takes the typed input and calls call MCP tool under the hood, which handles the actual MCP protocol communication. The function is documented with a comment, and it's properly typed for excellent developer experience. This is clean, readable, and exactly what developers expect when working with APIs. The code can read this file and immediately understand how to use the tool, what it expects, and what it returns. This also makes it trivial to add new tools or modify existing ones. You're just editing TypeScript files, not complex agent configuration. The file tree itself becomes the source of truth for available capabilities. Code execution in action. Now let me show you the dramatic difference this makes for actual agent operations. Remember our example from earlier. The user wants to download a meeting transcript from Google Drive and attach it to a Salesforce lead. Simple request. But look at what happens under the hood. First, the agent calls Google Drive to get the document. The full transcript, which could be tens of thousands of words, gets loaded into the model's context window. The model processes it. Then the model needs to call Salesforce to update the record, and to do that, it has to write out the entire transcript again as part of the tool call parameters. So that meeting transcript flows through the model's context window twice. For a 2-hour sales meeting, we're talking about 50,000 additional tokens. You're essentially paying for the model to read and write the same content multiple times, even though the model doesn't actually need to reason about most of that content. It's just moving data from point A to point B. And this is just a simple 2-step operation. Imagine a complex workflow with 10 or 20 steps, each passing large amounts of data through the model. The token usage balloons quickly.
Progressive disclosure. Let me dig deeper into each of these benefits, starting with progressive disclosure. The key insight is that models are genuinely excellent at navigating file systems. They understand directory structures. They can list files. They can read files selectively. We can use these capabilities to implement smart, on-demand tool loading. There are 2 main approaches. First, direct file system navigation. The agent can list the /servers directory to see what servers are available. If it sees Salesforce, it can list that directory to see what Salesforce tools exist. Then it can read specific tool files to understand their interfaces. The agent naturally explores the structure, loading only what it needs. The second approach is to provide a search tools function. The agent can search for relevant tools by keyword. For example, searching for Salesforce returns all Salesforce-related tools. You can even include a detail level parameter. Maybe the agent just wants tool names first, then descriptions, and only loads full schemas when it's ready to actually use a tool. Both approaches achieve the same goal. Instead of front-loading all tool definitions, we load them progressively as needed. For an agent connected to 1,000 tools, maybe it only needs 10 for the current task. That's a 99% reduction in tool definition tokens. And here's the beautiful part. As agents become more sophisticated and develop better intuition about which tools they need, they get even better at this progressive loading, further improving efficiency over time. Context efficiency. The second major benefit is context-efficient handling of tool results. Let me show you a powerful example. Imagine your agent needs to analyze a 10,000-row spreadsheet to find pending orders. With traditional tool calling, the agent would fetch the entire spreadsheet, all 10,000 rows, into its context window, then process it to find the pending ones. That's potentially hundreds of thousands of tokens for data that mostly gets filtered out. With code execution, the workflow is completely different. The agent writes code that fetches the spreadsheet into the execution environment, filters it right there using standard array operations, and then only logs a summary. The model sees found 47 pending orders, and maybe the first 5 rows as examples. The other 9,953 rows never enter the model's context at all. This pattern works for all kinds of data operations: aggregations, joins across multiple data sources, extracting specific fields from large documents, computing statistics, anything where you need to process large amounts of data, but only need to reason about a summary or subset. The execution environment becomes your data processing layer. The model writes the code that defines what processing should happen, but the heavy lifting happens outside the context window. Only the relevant results flow back to the model. This is particularly powerful for multi-step workflows. You can fetch data, process it, combine it with other data, process it again, and only present the final output to the model. Each intermediate step happens in the execution environment, preserving precious context space for actual reasoning. Control flow and privacy. Let me talk about 2 more critical benefits: better control flow and privacy preservation. On the control flow side, code gives you access to all the powerful constructs you're used to in programming. Need to wait for something to happen? Write a while loop. Here's an example: waiting for a deployment notification in Slack. The agent writes code that polls the channel history every 5 seconds until it finds a message containing deployment complete. Implementing this with direct tool calls would be incredibly inefficient. You'd need alternating get channel history calls and sleep commands with the model processing results each time. With code, it's a simple loop that runs in the execution environment. The model only sees the final deployment notification received. The same principle applies to conditionals, error handling, retry logic, parallel operations. All the standard patterns of programming become available to your agent. This isn't just more efficient, it's also more reliable. You're using battle-tested programming constructs rather than trying to orchestrate complex control flow through agent loops. Now, on the privacy side, code execution provides powerful guarantees. By default, intermediate results stay in the execution environment. The agent only sees what you explicitly log or return. If sensitive data flows through your workflow but never gets logged, it never enters the model's context. You can take this even further with automatic tokenization. The MCP client can intercept sensitive data like email addresses, phone numbers, or names and replace them with tokens before they reach the model. When that data is used in subsequent operations, the tokens get swapped back for the real values. The model never sees the actual sensitive information, but the workflow still executes correctly. This opens up whole new categories of use cases where you need to orchestrate operations involving sensitive data without exposing that data to the AI model itself. That's a powerful privacy guarantee. State persistence and skills. Let me talk about two more critical benefits: state persistence and the ability to develop skills. Because code execution typically includes file system access, agents can maintain state across operations. They can write intermediate results to files, enabling them to resume work after interruptions or track progress over long-running tasks. Here's a simple example: querying 1,000 leads from Salesforce and saving them as a CSV file in the workspace. Later, in a completely different execution, the agent can read that CSV back. The data persists between operations. But here's where it gets really interesting. Agents can also persist their code as reusable functions. Once an agent develops working code for a task, say converting a Google Sheet to a CSV file, it can save that implementation as a skill for future use. The agent writes the function, saves it in a ./skills directory, and can now import and use it in any future operation. Over time, the agent builds up a library of higher-level capabilities. Instead of writing low-level tool orchestration code every time, it can compose existing skills to accomplish tasks more quickly and reliably. This ties into the broader concept of agent skills, folders of reusable instructions, scripts, and resources that improve model performance on specialized tasks. You can add skill.md files to document what each skill does and when to use it. The agent learns to recognize patterns where a particular skill is applicable. This is powerful because it means your agent gets better over time. Early on, it's writing everything from scratch, but as it develops more skills, it becomes faster and more capable. The system evolves and improves through use. Now, I should mention an important caveat. Code execution isn't free. Running agent-generated code requires a secure execution environment with proper sandboxing, resource limits, and monitoring. These infrastructure requirements add operational overhead and security considerations that direct tool calls simply don't have. You need to carefully weigh the benefits, reduce token costs, lower latency, improve tool composition, better privacy, against these implementation costs. For simple agents with a handful of tools, the traditional approach might be perfectly fine, but as you scale up, the benefits of code execution become increasingly compelling. Implementation considerations. Let's talk about some practical considerations for implementing this approach. First, security is paramount. You're executing code generated by an AI model, which means you need robust sandboxing. The execution environment should be isolated with limited access to system resources. You need timeout mechanisms to prevent infinite loops. You need rate limiting and resource quotas. Anthropic has published detailed guidance on code sandboxing that you should definitely review. Second, think about your tool discovery mechanism. The file tree approach works great, but you might also want to provide search capabilities. A search tools function can help agents find relevant tools more quickly, especially when working with large numbers of integrations. Third, think about how you'll handle errors. Code can fail in many ways: syntax errors, runtime errors, tool failures, timeout errors. Your agent harness needs to catch these errors, present them to the model in a useful way, and allow the agent to debug and retry. This is actually one of the advantages of code execution. Debugging a piece of code is often easier than debugging a complex chain of tool calls. Fourth, think about observability. You'll want logging and monitoring to understand what code your agents are running, what tools they're using, and where bottlenecks where failures occur. The code itself serves as a useful audit trail of what the agent attempted to do. And finally, consider how this approach integrates with your existing infrastructure. If you're already using MCP servers, adapting them for code execution is often straightforward. You're just changing how the agent interface is presented, not the underlying tool implementations. Real-world results. Let me share some real-world validation of this approach. Cloudflare has published their own findings on what they call code mode, essentially the same technique we're discussing today. Their core insight aligns perfectly with ours. AI MLs are excellent at writing code, and developers should take advantage of this strength to build more efficient agents. They've seen similar dramatic improvements in token efficiency and execution speed. Other organizations implementing this approach have reported comparable results. We're talking about 10x, 50x, even 100x improvements in token efficiency for certain workflows. The benefits compound as workflows become more complex. A simple two-step operation might see 90% token reduction, but a 20-step workflow involving large data processing might see 99% reduction. The more your agent needs to orchestrate, the more valuable code.
Best practices. Based on our experience and community feedback, let me share some best practices for implementing code execution with MCP. First, start simple. Don't try to convert your entire agent system overnight. Pick a specific use case where you're hitting token limits or efficiency issues, implement code execution for that, and learn from the experience. Second, invest in good tool organization. A well-structured file tree with clear naming conventions and good documentation makes a huge difference in how effectively agents can discover and use tools. Think of it as API design. Clarity and consistency matter. Third, provide good error messages. When code fails, the agent needs clear information about what went wrong and how to fix it. Good error handling in your tool implementations pays dividends in agent reliability. Fourth, implement progressive complexity. Start with basic tool definitions and allow agents to request more detailed information as needed. This natural information hierarchy improves efficiency without sacrificing capability. Fifth, monitor and iterate. Watch what code your agents are generating. Are they discovering tools efficiently? Are they writing clean, efficient code? Use these insights to improve your tool organization and documentation. Sixth, consider providing code examples. Just as API documentation benefits from examples, your agent benefits from seeing example code for common patterns. These examples can be included in tool files or in a separate examples directory. And finally, engage with the community. The MCP community is active on Discord and GitHub discussions. If you're implementing this approach, these are great places to ask questions, share your experiences, and learn from others who are solving similar problems. The protocol and practices are still evolving, and community input is invaluable. Looking forward, as we look to the future, I think code execution with MCP represents an important evolutionary step in how we build AI agents. We're moving from a paradigm where agents make individual tool calls, essentially functioning as very sophisticated API consumers, to a paradigm where agents write programs that orchestrate multiple tools. This is a fundamental shift in capability and efficiency. As AI models continue to improve at code generation, this approach will become even more powerful. Models will write more sophisticated code, implement more complex control flow, and make better decisions about tool selection and data processing. We're also likely to see the emergence of agent-specific programming patterns and best practices. Just as we develop design patterns for object-oriented programming or microservices architectures, we'll develop patterns for agent code. How should agents structure error handling? What are the best ways to compose tools? How should state be managed across long-running operations? The concept of agent skills will mature.
We'll see libraries of reusable skills emerge, potentially even a marketplace where developers can share well-tested implementations of common patterns. Agents will increasingly build on top of existing capabilities rather than starting from scratch each time. Privacy-preserving computation will become more sophisticated. As organizations become more comfortable with AI agents handling sensitive data, the techniques for ensuring that data never enters model context will evolve and standardize. And finally, I expect we'll see convergence between traditional software engineering practices and agent development. The line between writing code and building an agent that writes code will blur. Developers will naturally think in terms of giving agents programming capabilities rather than just tool access. Community and resources. Before I wrap up, let me point you to resources if you want to explore this further. The MCP protocol has extensive documentation at modelcontextprotocol.io. This includes specifications, SDK documentation, and guides for building both servers and clients. The MCP GitHub repository at github.com/modelcontextprotocol contains the core protocol implementation, SDKs for multiple languages, and thousands of community-built servers you can use or learn from. Anthropic's engineering blog, which is where the article we're discussing today was published, regularly features deep dives into agent architecture patterns and best practices. The Cloud documentation also includes detailed guides on building effective agents. The MCP community is active on Discord in GitHub discussions. If you're implementing this approach, these are great places to ask questions, share your experiences, and learn from others who are solving similar problems. Cloudflare's blog post on code mode provides an independent validation of this approach with their own examples and insights. And if you're interested in the broader topic of AI agent architectures, there's a growing body of research and practical experience being shared across the industry. This is a rapidly evolving field, and staying connected to the community is valuable. Summary and conclusion. Let me bring this all together. We started by understanding the challenge. As AI agents scale to interact with hundreds or thousands of tools via MCP, traditional direct tool calling creates serious efficiency problems. Tool definitions overload the context window, and intermediate results consume excessive tokens. These aren't hypothetical issues, they're real bottlenecks limiting what we can build. The solution is elegantly simple. Present MCP servers as code APIs and let agents write code to interact with them. This approach leverages what AI models do best, generating code to solve efficiency problems in agent architectures. The benefits are substantial and multifaceted. Progressive disclosure means loading only needed tools. Context efficiency means processing data outside the context window. Better control flow means using established programming patterns. Privacy preservation means keeping sensitive data out of model contexts. And state persistence means building up capabilities over time through skills. The real-world results speak for themselves. 98% token reduction in some cases, dramatic cost savings, improved latency, and unlocked use cases that weren't previously feasible. But this isn't just about efficiency. It's about enabling a new generation of more capable, more reliable, and more scalable AI agent systems. As we move forward, code execution with MCP will likely become the standard approach for sophisticated AI agents. The technology is ready, the community is active, and the benefits are clear. If you're building AI agents that need to interact with multiple tools and systems, I encourage you to explore this approach. Thank you for your attention, and I'm happy to take questions.